In this lecture, we are going to look at training methods for linear classifiers, and in particular, the minimum distance method. We will then use that material to help us understand and develop training methods for more complex classification techniques. Remember, we are assuming at this stage that the two classes of pixel that we are dealing with are linearly separable. That is, a straight line can be placed between them. Many datasets, however, are not linearly separable. We will meet some later, but recall for the moment that the maximum likelihood classifier is able to separate datasets with at least quadratic hypersurfaces. There are many acceptable linear decision surfaces that can be placed between two linearly separable classes, as illustrated in this slide. One of the earliest methods for training, which goes back to the 1960s, involves choosing an arbitrary linear surface. That choice will almost certainly not be in the right position, in that it will not have the classes on the right sides of the hyperplane. But then, by repeated reference to each training pixel in turn, the hyperplane is gradually iterated into an acceptable position. The book by Nielsen, referenced here, shows that method in detail. Note a restriction, however. We are only dealing with two data classes. We will have to embed this method into some form of multi-class process later on. A better approach might be to choose as a separating hyperplane that which is the perpendicular bisector of the line which joins the means of the classes, as shown here. We can find that line as the locus of the points that are equidistant from the two class means. Note that we use the nomenclature d bracket x comma m subscript I close brackets to represent the distance vector between 2 points. If the distances are equal, then so will be their squares, saving the need to compute the expensive square root operation in software. So we equate the squares of the two distances from a position x to the class means, leading to the equation of the linear surface at the bottom of this slide. Note that it has the same structural form as the equation of a straight line that we are familiar with in 2 dimensions. Note also that we have had to use 2 vector identities in coming to this result. Although we have computed the equation of the decision surface, in the minimum distance rule, we actually don't compute the hyperplane explicitly. Instead, to label an unknown pixel, we just compare the distance squared to the class means and allocate the pixel to the class of the closest mean. That suggests that we can actually account for as many classes as we need to. In this slide, we have shown 3 classes and given a general decision rule for the minimum distance classifier. So in summary, for the minimum distance classifier, 1. Training data is used to estimate the class means. Fewer pixels are needed compared with the maximum likelihood classifier, since no covariance matrix estimation is required. 2. Unknown pixels are allocated to or labelled as the class of the closest mean. 3. It is a multi-class technique. And 4. It is fast in both training and classification. We are now at the stage where we can look in summary at the 2 classifiers we have treated so far and see the steps the user follows in practice. Although in our lectures we have looked at the mathematics of the techniques, you do not need to know that material in practice, although it does help you understand how the algorithms work and their comparative limitations. Note that 3 of the steps are common to both approaches, as highlighted in blue, and will also be common to any of the classifiers we look at in this course. They are training, thematic mapping, and accuracy assessment. The approaches differ only in how the classifiers are trained and how they are applied to unseen pixel data. If class conditional probabilities are used with the maximum likelihood method, there is an assumption that prior probabilities are available. Again, the software looks after that step, provided the user can assign values to the priors. Note particularly the last step. Rarely, in a real classification task, will the accuracy on all classes be acceptable the first time around. Instead, the analyst may have to consider whether some classes have been missed, leading to their pixels being misallocated to another class, or whether some classes are too broad spectrally and should perhaps be subdivided into constituent subclasses or spectral classes. Again, we will have more to say about this when we look at classification methodologies in Module 3. We are going to meet a number, but not all, classifiers that are used regularly in remote sensing. Some are quite complex and require a lot of user effort to make them work effectively, but they can give exceptionally good results. When selecting a method, though, it is important not to go overboard in always choosing the newest and potentially the most complex one. Often the simple algorithms will work just as effectively in many real-world applications. Remember what we said at the start of this course. While we are necessarily spending a lot of time developing classifier algorithms, our course objectives are remote sensing and its applications, so we need to keep that in mind when evaluating classifier methods. Ultimately, we will have to embed them into a methodology, which we will do in Module 3. The first two questions here just test your knowledge of vector algebra, while the last two set you up for what is to come.